Good afternoon, everyone, and welcome to IBAAS 2023 Technical Lecture Series. I am Dr. Suchita Rai from Jawaharlal Nehru Aluminium Research Development and Design Center, working as a principal scientist. And the presentation topic today is Special Hydrates and Aluminas, its properties and applications. The contents of the presentation are Introduction to Bayer process, then classification of hydrate and alumina, applications of special hydrate alumina, and characteristics of aluminium hydroxide. We would be also looking into ATH as fire retardant fillers, where we would be discussing on nano ATH, Oni's grade ATH, and then we would be moving on to activated alumina, calcined alumina, tabular alumina, fused alumina. And we would also have a look into how caustic is incorporated into the alumina, while the reactive alumina and high purity alumina also play a great role in our day-to-day life. We would also be looking into prices of special hydrated alumina, how they vary according to their particle size and their purity. And then the products developed at JNR DDC would be discussed. The introduction to Bayer's process, the left hand side we can see the alumina refinery, while on the right hand side shows the Bayer's process. In the Bayer's process, bauxite is the primary ore of alumina, which is first ground along with the steam and caustic soda solution. After that it goes into pre-desiccation where silica is removed, and then the whole of the slurry is forwarded into digestion where green liquor is added into it at an elevated temperature of 145 to 240 degrees centigrade, depending upon the characteristics of the bauxite, that is the mineralogy, basically the mineralogy of the bauxite. After the digestion process, the mud slurry or the whole of the slurry, it is separated into the mud as well as the pregnant liquor, which goes into security filtration for separation of iron, very fine iron particles into it. And then it goes into the precipitation where the aluminate liquor is cooled down to about 60 to 70 degrees centigrade, after which the hydrate which we get is in the product form. The fines are separated as seed, which is recirculated into the precipitation process, and the product after classification goes into washing and filtration, and then it goes into the calcination for the production of alumina. Now here, after we get the hydrate, it is classified into two categories. 90% of it goes into the production of aluminium metal, which is called as the metallurgical grade alumina, while the non-metallurgical grade alumina, which is 10%, it is used for production of special products. Now, which are these special products? We would be saying this into detail. Now, the first of all, as I said, the Bayer process produces hydrate, which 90% goes for production of alumina, while the rest 10% goes for non-metallurgical grade special products. In this 10%, it is classified into aluminium trihydroxide and alumina, in which the 60% of it goes for aluminium trihydroxide and activated alumina. Aluminium trihydroxide basically is used in chemicals, flame retardants and fillers. Activated alumina, as they are used in absorbents, catalysts and desiccants, and the 40% of it goes into calcined alumina, which is used in abrasive ceramics and refractories. So this is the outline of the bare alumina as well as the special products, hydrates and alumina. If you see the details of applications of special hydrate and alumina, aluminium hydroxide basically used in chemicals, fillers, flame retardants and pharmaceuticals. They are used as antacids. Activated aluminas, they are used as adsorbents, catalysts, desiccants and also decolorizing agents. Calcined alumina also has vast applications in abrasives, ceramics, refractories, in production of tabular and fused alumina, while the tabular alumina, which are basically produced at 1600 degrees centigrade and has a very high hardness, that is more than corundum. It is used in high-end refractories, electric insulators, ceramic parts. Fused alumina, which are used in abrasives, in ceramics, and high purity alumina, which has high-tech applications in nuclear ceramics and in specialist electronic components. So how hydrate converts into alumina? Basically, from the alumina trihydrate, when it is calcined to around 1100 degrees centigrade, it goes for the production of metallurgical grade alumina, which finally goes into the smelter, and it is also calcined to get a soda content of 0.3 to 0.6%. After suitable treatment, this 0.3 to 0.6% reduces to 0.1%, and then it has various applications in abrasives and refractories. While the high purity for alumina which are produced from non-wear alumina, they have soda content of less than 0.01%, and the other impurities are present in ppm level. If you see the characteristics of aluminum hydroxide, they are classified into normal grade, fine grade and ultra fine or superfine grade. Now these are classified basically based upon the particle size. That is, normal grade has a particle size of D50 30 to 70 microns, fine size has 3 to 25 microns, and ultra fine or superfine has the particle size of 0.6 to 1.5 microns. Now from here we can see that the source of normal hydrate, it is aluminum hydroxide. That means this aluminum hydroxide is the same which we get from the bare alumina, after which it is ground to get a particle size to 3 to 25 microns, and then this 0.6 to 1.5 microns cannot be produced by grinding because it requires a very high grinding energy into it, and hence it is produced by special precipitation technique. Now the other thing which we have to look into it is that though the other characteristics, other components, that is the iron content, silica content and the soda content are nearly the same, that is 0.01 to 0.02%. In all the three components, the soda content in ultrafine and superfine is slightly above the normal and fine hydrate, that is 0.3 to 0.54%. And this is basically due to the special precipitation technique, due to which the seed is produced and then it is incorporated into sodium aluminate liquor. Then again, the other thing which we have to see specifically here is that the applications depend upon the particle size. Now the application of feedstock for manufacture of aluminium salts, glass ceramics and catalyst industries, they need a particle size of only about 30 to 70 micron. But if it is going to be used in rubber, chemicals, cables, plastics, foams and carpets, it needs a particle size of about 3 to 20 microns. Even for the application in paper, in toothpaste or in synthetic marble, the whiteness should be above 92%. And hence, if we grind it, the whiteness increases because the structure of the aluminum hydroxide, which we find here, which it is a very regular structure, it is hexagonally shaped. This structure opens up after grinding, and this whiteness increases, and it increases up to greater than 92%. And hence then they can be used in paper for increasing the whiteness of the paper, in toothpaste as they are used as abrasives in toothpaste, and synthetic marble for increasing the translucency of the material. Then if it is about the 0.6 to 1.5% micron size, that is ultrafine and superfine hydrates, it is used in special paints, pigments, inks, pharmaceuticals, electronics and as fire retardant fillers in flexible plastics. Now here you can see that the particle shape is very regular as compared to the fine grade. That is because it is produced from the special precipitation technique. Here we get a very regular particle size. So how ATH is used as a fire retardant filler? It is used basically due to its physical and electronic properties, cost effectiveness, high versatility and portability. And the market shows that 50% of the flame retardants which are sold worldwide are inorganic hydroxides, and ATH is the largest flame retardant used. Now what happens when the polymer burns? ATH releases water vapor, that is at around 210 to 300 degrees centigrade. The water vapor which is present in the ATH, it is released and it reduces the polymer surface temperature. And as the surface temperature increases, it acts as a heat sink and lowers down the whole temperature of the polymer. And these polymer based materials are the key components in many important industries such as construction, automotive, electronic and aerospace. Now if we see the fire triangle, in this fire triangle the burning of polymer is, when the polymer burns, when there is a fire, it is very rapid. And as it is rapid, the process is exothermic also, liberating a very high energy. It is due to the oxygen induced degradation process of the polymer. And this fire is initiated by heat, by the high temperature, which decomposes the polymer into combustible gaseous species. And when this decomposes, it decomposes the polymer into combustible gaseous species. There are formation of hydrogen radicals, and when these hydrogen radicals they combine with oxygen molecules, they further create free radicals of O and HO. They react with carbon monoxide exothermically, which now this propagates the chain reaction, which causes additional burning of the polymer, and this whole reaction is interrupted by the flame retardants. And this flame retardants also suppresses the soot formation and the further formation of chemical species. In this way, the flame retardants retard the whole burning process, and in the process the soot formation, the toxic gas formation, they are also retarded. Now here we are seeing the nano ATH and how nano ATH is preferable, or the fine size is preferable as compared to the coarse size. So what happens when the coarse ATH is loaded into the polymers? They are loaded in a high loading of about 40 to 50%, and when they are loaded in this proportion, the dispersion is uneven. Here you can see the dispersion of this fire retardant fillers in the polymer is uneven, and which causes the volatile flammable volatiles. We can see the fire quantity which we can see here, it is enormous when we are using the coarse ATH. And due to this coarse ATH incorporation into the polymer and due to the uneven dispersion, this reduces the workability and physico-mechanical properties of the polymer, and this causes the tensile properties get affected and the brittleness of the polymer increases. So for this, the fine size ATH or nano size ATH has been proposed to be incorporated into the polymers. Due to this, you can see if we compare the fire here, this is in the much reduced form, as it is uniformly disperses, and it is the dispersion we can see here, it is quite good, and this causes better tensile properties which can be achieved by the incorporation of uniform dispersion of nano size polymers while maintaining the fire retardant properties. And this here we have achieved in JNRDDC, which we have got by high energy planetary ball mill. The nano size of the particles, it is around 50 to 350 nanometers, which we have got in our same picture. We can see here that the nano size achieved here is about 78 to 189 nanometers. Now how this nano ATH is incorporated into the polymer? This polypropylene with the compatibilizer, that is maleic anhydride polypropylene plus ATH nano or micro size, it is mixed in batch mixing at temperature of 190 to 200 degrees centigrade, which is finely shredded into a small size, and we have to do injection molding. And here you can see the batch mixing of this compatibilizer with the polypropylene and nano size ATH, the compounded material with nano and micro ATH and MAPP, which goes into micro injection jet and the compression mold, and finally the polymer, which is fireproof, is prepared. Now the other grade which we are carrying out is the onyx grade ATH. Onyx grade ATH means synthetic grade ATH, which requires a very high whiteness of 96, greater than 96%. And this cannot be produced from the bare ATH by grinding, because the bare liquor consists of impurities. As we have seen in the bare process, the bauxite which contains organics, which the organics are formed into the bauxite due to its formation which has taken place in the millions of years, and the other organic materials have been forming into the bauxite. That's why these impurities come into the bare liquor when they are treated with caustic soda solution at elevated temperatures, and they cannot be removed by simple process. And the conventional process which is followed is the sintering process, which is highly energy intensive to remove organics. And even though if it is there, the ATH which we get, it has less whiteness with Fe2O3 and silica content of 0.015%. So the pure and white ATH, which is a synthetic grade marble, grade, it is produced where the bare liquor should be very pure, and it is produced by a different process where we do not get the organics into the liquor. And apart from that flame retardancy, this ATH filler imparts a marble-like translucency to the cast acrylic, and it can be used in kitchen counters and bathroom panels. And due to this making of onyx grade ATH, the natural resource of marble, which is depleting day by day, it can be avoided. And this onyx grade ATH has a very high purity of, that is 0.005% silica, 0.008% of silica less than 0.08%, and Fe2O3 is 0.005%, but soda is less than 0.25% with D50 of 20 to 30 microns. Now we would be moving into a different category of activated alumina. As I said, the 60% of non-metallurgical grade alumina, in which about 40% is the ATH and the 20% is activated alumina, it is formed by transition phase of aluminium oxide. That is, it is a transition phase of aluminium oxide. It is produced by heating aluminium hydroxide to a temperature of about 250 to 700 degrees centigrade, and it is also called as a thermal dehydration of aluminium hydroxides, and it can be produced in different ranges. The temperature ranges from 250 to 700 degrees centigrade, as I said, and it is highly porous structure because the molecular water is driven out by heating the hydroxides, leaving behind a highly porous structure, and it also has a very high surface of about 275 to 350 degrees centimeter square per gram. Now this it is easy. This surface area can be achieved by heating the aluminium trihydroxide to about 400 to 450 degrees centigrade to 300 meter square per gram, but it is difficult to go above 300 meter square per gram because it requires a heat energy which is called as flash calcination, and that is it is for a very few seconds which we achieve the surface area above 300 meter square per gram, and this is a requirement in health sector, basically to remove the moisture from the oxygen, which we have seen during the COVID times. We have seen that oxygen cylinders were required, and a disease had come where it was affecting the eye, and that was because of the moisture content which was present in the oxygen cylinders. So there the demand increased because the this surface area, which is about greater than 300 meters square per gram, it requires a flash calcination process, and again it has a very high absorbing property which absorbs the moisture in the oxygen or other gases also, such as hydrogen. It can absorb the moisture present in it. And the principal use, as I said, it is in drying agents, in adsorbents, catalysts and catalyst carriers, and mostly it is used for absorbing moisture, water vapor, humidity and odor, and it is used in drying of gases such as oxygen, hydrogen, nitrogen and carbon dioxide. And the properties of the final product, that is the final active product, it depends upon the physical and chemical nature of the starting hydroxide and thermal dehydration properties and the history of the product. So these are highly customizable. These activated alumina can be produced according to the uses, according to the surface area required, and the product can be developed specifically for air drying, which should have optimized characteristics, and it should be in sphere size. And mostly the sphere size ranges in between minus 45 micron, 2 to 5 mm, 2.5 to 5 mm and 4 to 8 mm. And it has a great effect in polluted water. It can be used, and the polluted water, as we have seen, it has negative effects on public health, and hence it is imported. Imported activated alumina they are mostly in 45 micron size, 6 to 8 mm and 3 to 5 mm bead size, and they can be taken as adsorbent for water purification process and also for drying. So mostly these products are activated, but in India some industries are also making. So the product demand lies for clean water, shrinking water reserves and the implementation of new water treatment facilities, and the government initiatives such as launch of various projects for the regular and supply and treatment of water are likely to propel the product consumption by 3 to 12%. And they are used in water treatment infrastructure, and the increasing demand for oil and gas application are key drivers for global activated alumina market. Now we would be looking into the thermal dehydration of alumina hydrates. So first of all, how does this thermal dehydration of alumina hydrates varies from gibbsite, that is from trihydroxides, to monohydroxides, that is from gibbsite to boehmite and dispar. Now when we heat the gibbsite to 300 degrees centigrade, about 300 degrees centigrade, the transition phase which is formed is Ki alumina. This at 700 degrees centigrade we get as kappa alumina. At 1100 degrees centigrade alpha alumina is formed. While the monohydroxide, that is the bohmite, it gives gamma alumina instead of Chi alumina. When bohmite is treated at 300 degrees centigrade, the gamma alumina is formed, which has high application in adsorbents, and when it is heated to 800 degrees centigrade, delta alumina is formed. And finally at 1000 degrees centigrade, theta alumina is formed. At 1100 degrees centigrade, alpha alumina formed. So both the gibbsite and the bohmite to give alpha alumina 1100 degrees centigrade is necessary. But diaspore at 500 degrees centigrade only gives alpha alumina. So this is the complete thermal dehydration of aluminum hydroxide. So if we see if we have seen the graph of LOI reduction and the surface area increase with respect to temperature, we can see as the temperature increases, the surface area increases up to a certain point of about 700 degrees centigrade. But as this temperature is increased to 1100 degrees centigrade, the pores which are formed, the porosity of the activated alumina, it get reduced, and then the fully shrunk structure is formed of the material is formed, which is called as alpha alumina or the calcined alumina. So the powdered activated alumina, they are heated. It is formed by heating alumina hydrate to 300 to 750 degrees centigrade, where the surface area formed is 200 to 350 degrees meter square per gram with LOI of 3 to 12%. And the uses are in decolorizing agents for organic chemicals. The starting materials, they can be used for starting materials for the production of aluminum fluoride. They are used in chromatography and catalytic applications in organic chemistry. There are also granular activated alumina. They are produced by heating the precipitated or hydrate to 400 to 600 degrees centigrade in hot air or in flue gas stream. They can be categorized in F1, H151. These are the nomenclature given by different industries which produced activated alumina. And here you can see the alumina content is 92 to 95%. With the soda content is quite slightly high, about 0.5%. With silica and Fe2 content of 0.12 and 0.06%. LOI we can see it is 76 or because it is about 600 degrees centigrade. The LOI is 6.5%. With the loose and packed bulk, the bulk density, pore volume and total porosity is very high, that is about 59 to 60%, with the BT surface area ranging from 250 to 360 meter square per gram. And this activated alumina application is in drying and purification of air, which is used in healthcare. Now, the production of activated alumina from bohmite and gelatinous aluminum hydroxide, they are basically used for catalytic application, and here no soda is permissible because they are used as catalyst, and the activated temperature is 500 to 600 degrees centigrade with specific surface area of 185 to 250 meter square. There are alumina gels also, which are produced by neutralization of aluminium sulfate or ammonium alum using NH3 or from sodium aluminate by neutralization with acid CO2, NaHCO3 and aluminium sulfate, and the gels are activated to 400 to 600 degrees centigrade to get a specific surface area of 300 to 400 meter square per gram with LOI of 3 to 4%. Here you can see the surface area can be reached up to 400 meter square per gram using this alumina gel. Now specialty calcined alumina, as I said, when we increase the temperature of 1000 degrees centigrade, a fully shrunk material is formed, which is very hard, and it is formed at a fairly high temperature above 1000 degrees centigrade, and the major utilization is in ceramics, that is 20 to 30%, in refractories 50 to 60%, and in abrasive 15 to 20%, in others 3 to 4%. Now the characteristics properties of calcined alumina are, they are basically classified based on soda content, that is the normal soda, intermediate soda and the low soda. Now normal soda, that is by calcination of normal ATH at a temperature of 1000 degrees centigrade, we get a soda content of about 0.2 to 0.25 to 0.4%, but the intermediate soda is 0.15 to 0.25%, and the low soda is 0.1%. As we had seen in ATH that the classification is based upon the particle size, here the classification of calcined alumina, it is based on the content of soda which it is having, that is the range should be below 0.4% for normal soda, it should be below 0.5 to 1.25 in intermediate, and low soda, that is 0.1%. So the application depends upon the soda content. That is, this range of normal soda, it can be used in abrasives, in glass, electrical, porcelain, sanitary waste, and tabular and white fused alumina manufacturing. While intermediate soda, it is used in special applications of electrical insulators, electroporcelain, in high voltage supporting insulators, in refractories and electronic ceramics. While the low soda, it is used in spark plugs and sodium vapor lamps. Here we can see the other properties. Alumina is 99 to 99.6%, 99.5% and 99.8%. And if the soda content is below 0.1%, like if the impurities are it is soda 0.07 to 0.8%, we can get a soda content of 99.9% also. Sorry, alumina content of 99.9%. That is 3N alumina is produced by this method. Now the physicochemical properties we can see is that the alpha content is greater than 90%. In intermediate soda it is 95 to 98%, while for low soda it is greater than 95%. And obviously the LOI at 1100 degrees centigrade is only 0.1 to 0.2%, less than 0.1%, and 0.05 to 0.15% for low soda, while the specific surface area here it is 4 to 7 meters square per gram. For intermediate is 0.4 to 0.7 and 0.5 to 0.8%. Sorry, meter square per gram. Now we have to see here how this origin of soda occurs in calcined alumina. Soda basically is there in three forms. That is, the caustic soda, during precipitation we have seen that the temperature given is about 60 to 70 degrees centigrade, and the temperature time also given is about 40 to 60 hours. During this time, this caustic soda gets adhered to the surface of the ATH, and it can be reduced by washing to a certain extent. But the other soda, caustic soda, which is into the sealed in by the crystal growth of the particles, it cannot be removed, because the soda which is adsorbed on the surface can be removed by washing or by a slight addition of acid to it, but the which is sealed into the crystal growth, which is also called as the bound soda, it is very difficult to remove. One of the method is that to partially calcine it, so that this soda comes on the surface, and then washing it, washing the hydrate activated alumina, so the soda can be reduced to about 0.1% by this process. And the third step in which the soda is incorporated into the hydrate is the co-precipitation of salts like sodium vanadate, sodium oxalate, and the other salts which are formed into the Bayer process along with the hydrate. So this is the origin of the soda, and some partial reduction of soda can be done by washing, but the soda which is adsorbed, which is incorporated into the crystals, cannot be removed. So there are certain methods for soda reduction where the soda can be reduced to some extent. One of the method is the special operating condition during precipitation. That means during precipitation only the soda incorporation should be less. That is, the bound soda can be reduced if the precipitation temperature is increased to about 90 degrees centigrade and the supersaturation is low. But here, if the supersaturation of the liquor is low and the temperature is high, the liquor productivity decreases. That means we have to compensate on the liquor productivity. But as I said, the value addition of the low soda product is very high. That is, the soda of the product containing 0.3 to 0.4% will have a very less market value as compared to a product which is having the soda content of less than 0.1%. Nearly 3 to 5 times of value addition is there. So even though we have to compromise on the liquor productivity, if the product whichever we are getting is having a low soda content of 0.1%, the properties which we achieve in low soda content alumina, it has a very high value addition, and that's why it is preferable to give a high temperature in the precipitation step, and low supersaturation can be kept in the precipitation process. The other method is leaching out soda from partly or fully calcined bare alumina by water or dilute acids. Or also some literature is also there on using coarse grained silica minerals to remove soda from the bare alumina. Also the hydrothermal conversion of bare hydroxide or gibbsite to the oxide hydroxide bromide also causes less soda into the process. Now when we come to tabular alumina, that means tabular alumina is a highly dense, high strength form of pure sintered alumina which is made by high temperature sintering of an agglomerated shape of ground hard calcined alumina. That means the calcined alumina which we have got at 1100 degrees centigrade, it is ground, it is formed into certain shapes, and after that it is sintered at a high temperature of about 1600 degrees centigrade, and the crystals which are formed, they have 50 to 400 micron size and can be seen through the naked eye, and it derives its name from the large the typical micron size of the crystallites which are formed. Flat corundum they are flat corundum crystals that are formed during the sintering and constitute the sintered shape. These are large crystal facets which can be seen by the naked eye. The temperature is about 1600 to 1800 degrees centigrade, and this produces a fully shrunk material which has a very high hardness and very less porosity of 2 to 3%. And this unique structure makes it distinctly different from other dense fine crystalline sintered aluminas and from fused alumina, and this is the typical characteristics of the tabular alumina, which is characterized by retention of closed spherical porosity approximately 10% and nearly complete elimination of open porosity, that is in only 2 to 3% residual porosity. And the characteristic properties of tabular alumina is that it contains alumina percentage is 99 up to 99.5% with silica of 0.04 to 0.06%, with soda to 0.1 to 0.3%. Alpha alumina is greater than 90%, and grain size is 50 to 400 microns with very less BET surface area 0.1 to 1 meter square per gram. The bulk specific density is very high, that is 3.5 to 3.65 grams per cc with hardness on Mohs scale as 9. Now as it is very hard, it has the strength of the grains of tabular alumina is 1 to 3 times higher than that of corundum, and hence it is used as a component of refractory bricks, concretes and masses in the iron and steel industry, in the metallurgy of other metals, cement lime industry, ceramic industry, chemical and petrochemical industry, in the energy production and heating element bricks. The other category of special alumina is fused alumina, that is brown fused alumina and white fused alumina. Brown fused alumina is produced from the calcined bauxite which contains more than 80% of alumina and which is used for the production of brown fused alumina. It contains 95 to 97% alumina. The other impurities being titanium oxide, silicon oxide and Fe2O3. And to obtain greater than 95% Al2O3 from calcined bauxite containing about 85% alumina, reducing agents such as coke and anthracite are added to reduce Fe2O3 and silica and partially TiO2 to the metal. And the abrasive industry is the biggest consumer of brown fused alumina. Now coming to white fused alumina, it is produced from bare calcined alumina in a continuous furnace, and the melt from continuous furnace is poured into water cooled cast iron, steel or aluminium molds, and the important applications are in abrasive and refractory applications. And the variation can also be done in white fused alumina as pink and red fused alumina, which is formed by the addition of chromium oxide, which improves certain abrasive properties of this alumina. The properties exhibited are they have a density of 3.97, Poisson's ratio of 0.27, with the hardness, Knoop hardness of 2100, modulus of rupture that is 275 to 555, with electrical resistivity and thermal conductivity very high, and melting temperature is 2050 degrees. Now the other aluminas which have special applications are the reactive aluminas, and these reactive aluminas are formed the commercial scale fabrication of high performance plus 19% alumina technical ceramics which is suitable for industrial applications in ceramics, and they are derived from low soda aluminas which are having 0.1% Na2. And how they are formed? They are sintered at 15 degrees centigrade and then super ground to a fine crystalline alumina size of less than 1 micron size. The methods of the other categories high purity alumina, and the methods of production are from aluminium salts, that is thermal decomposition of aluminium salts, precipitation of aluminium hydroxide from aqueous solution, from aluminium metal, that is direct oxidation with oxygen, reaction with water, and from decomposition of organometallic complexes, that is thermal decomposition, hydrolysis to aluminium hydroxide. Now if we see one by one, from the aluminium salt, that is thermal decomposition of aluminium salts, the salts which are used for thermal decomposition at 1000 degrees centigrade are ammonium, aluminium, and alum, aluminium nitrate, aluminium chloride, aluminium salts of organic acids such as aluminium oxalates and acetate. The product after calcination at 1200 degrees centigrade consists of fine 0.1 to 0.25 microns of alpha alumina particles. The other method is precipitation of aluminium hydroxide from aqueous solution, that is aqueous solutions of aluminium sulfate and nitrate are neutralized using ammonia, ammonium hydroxide, urea and formamide, resulting in precipitation of aluminium hydroxide, which is then calcined to form aluminium oxide. From aluminium metal, that is direct oxidation with oxygen in air or oxygen atmosphere at 800 degrees centigrade, which is a highly exothermic reaction, and about 400.2 kilocalories of heat is liberated in this. And again the reaction with water, which produces hydroxide with the simultaneous evaluation of hydrogen. You can see the aluminium metal, it is giving 1.5 H2, and in the process which is developed by Alcoa, the aluminium powder is reacted with choline solution at 50 to 80 degrees centigrade to yield crystalline aluminium hydroxide, which is then calcined to yield alumina, and then this is used to produce high purity alumina, which are used for special. Now other method is decomposition of organometal complexes. The aluminium forms compounds with most alcohols. In general, the formula is Al thrice, where R represents the alcohol change. And the decomposition of alkoxides can be achieved either by thermal decomposition, that is 800 to 1000 degrees centigrade in nitrogen atmosphere, or by hydrolysis with water. And the thermal decomposition occurs by this reaction, where we get alumina, and R dash is an olefin such as ethylene, propylene and butylenes, and the product which is formed is very fine, which is 0.2 micron size of amorphous aluminium oxide. And the other method is hydrolysis to aluminium hydroxide. The aluminium alkoxides give the highest purity, that is a finite alumina, that is 99.999% uniform size alumina, which is formed by this process. The chemical composition of high purity alumina is that we can see the alpha phase, that is the crystal phase, is greater than 90% gamma, 85% alpha, and the purity is here, it is 4N, that is 99.99%. The other impurities which we can see is sodium, it is 20 ppm, lead, chromium and zinc is 4 ppm, silicon is 18 ppm, iron and calcium 10 ppm, gallium 15, magnesium and titanium less than 5 ppm, and we can see the composition, that is SiO2, Fe2O3, CaO, Ne2O, they are all less than 10 to 50 ppm. So we can see the purity of the this alumina is very high, where all the impurities, that is the iron, silica, titanium, calcium, sodium, they are all below 50 ppm. That's why they are called as high purity. And the characteristic properties of high purity alumina is the ultimate particle size, that is in micron, is 0.01 to 0.15 and less than 0.5 micron. Specific surface area is high, that is 115, because the particle size is very less and it is produced by special methods. The specific surface area is high, that is 115 meters square per gram, and the calcined part is the other is 10 and 50 to 50 meters square per gram. The agglomerates, the micron size are 2.6 and 0.5. Crystal density is very high, that is 3.98 grams per centimeter cube, and apparent bulk density is also it is very less, that is 0.1 to 0.51. This should be grams per centimeter cube. Now if you see the application of high purity aluminas, they are all in high-tech areas, that is analytical instruments, that is typical applications in HPLC pumps, piston balls, seats, rotors and stators for injection balls, pump heads, etc. Precision dispensers, and then in medical instruments they are used in ophthalmology, in endoscopy, microtomy, electrosurgery, components for implantable devices and dental applications. So they have vast use in medical instruments. Then electrical and electronic materials, they are active, active and passive electronic components such as resistors, capacitors, hybrid circuits, cameras, sensors and other critical devices which are used in automotive electronics, satellite and telecommunications, medical equipments and biotechnologies, servers and components. In they are also used in navigation and submarine. That is, precision ceramic parts are required for excellent performance, for bearings for navigation, instruments and insulator for accelerators. For submarines, they are also used in transmission of sound, that is the high-tech ceramic transit sound, better than other metals used in traditional transducers. In abrasives and refractories, it is the basis for most important polishing agents for industrial and private use. It is used to polish the hard drive in the computer as well. They are also used in aerospace industry, in satellites and spacecrafts. High alumina rod tubes are used in turbines of jet engines to withstand high temperature and to provide wear resistance. And the other industries where high aluminas are used they are used in processed foods and beverage industry, in oil and natural gas exploration industry, in chemical and refinery industries. And alumina in transition forms are used as paper, anti-skid coatings, polymer additives, thickness rheology, modifiers and wash coats for exhaust gas catalytic converters. So you can see that high purity aluminas, they are having high-tech applications in these varied fields. Hence there is a market for this product, and it has to, they are mostly imported, these products are mostly imported, and the need of the hour is that this high purity aluminas to be produced in India in by various techniques, where the whatever inputs are required for these applications can be provided in India itself. Now, if we see the prices of special grade alumina, here there is a comparison with the smelter grade alumina, in which we have seen the activated alumina, which has a high porosity, which are high surface area, which are used in catalyst surfaces. They are used as catalysts in adsorbents, in water purification, in absorbing gases such as moisture in various gases such as hydrogen and oxygen. They have a very high value addition, that is 5.9 to 8.2%, 8.2. That means if the normal ATH, it is having a market of about 20,000 rupees per ton. This activated alumina at 8 times, it is about 1,60,000 rupees per ton. So the variation in the market product, it is very high. Only by, like, if you make a product which is activated, that means it is high surface area, by heating it, by washing it to a certain extent, if it is having a low soda content, it is having a very high value addition of about 5 to 8 times that of smelter grade alumina or hydrate. Now if it is used as catalyst grade, here you can see the variation, it is about 26% higher. It is about 26% higher, 26 times higher than the smelter grade alumina. Then the abrasive grade, if we see, it is the abrasive grade is 2.1 to 3.6 times. The refractory grade is 1.5 to 3.3 times that of smelter grade. The spark plugs is, here you can see, it is having a 20 times value addition than the smelter grade, because in spark plugs and electronic ceramics and in special applications, as we have seen, they require about 99.99% of purity, and hence they are supposed to be used in these applications. So at JNIDTC we have developed special products. They are ultra-fine headed, that is 1 to 2 micron size. We have produced here by special precipitation technique, aluminum hydroxide. Low soda headed, that is less than 0.1% soda. 3N alumina, 99.9% of alumina. Fine headed, 10 to 12 micron size, we have produced through precipitation process. Because in some of the applications, regular size of structure and morphology is required, and so to produce 10 to 10 micron size through precipitation route, we have produced it here, where in certain applications like in cables or in wire applications, they require a very regulated size of or very good morphology of the hydrate. Nano size ATH of 50 to 350 nanometers for fire retardant fillers we have made here. We are in the process of making onyx grade ATH. High alpha content alumina greater than 99% we have produced here, and activated alumina of having 90 to 100 micron size as well as 10 to 12 micron size. High surface area of 250 to 300 meters square per gram we have developed at JNIDDC. The bohmite hydrate which has had the bohmite that is having 90 to 100 micron size and 10 to 12 micron size we have produced in our laboratory, and the gamma alumina of 100 to 110 meters square per gram we have been able to generate here, and we have also filed a patent. We have a patent have been granted to us to produce smelter grade alumina from bohmite hydrate. So these are various achievements of JNIDDC where we have produced special hydrate and alumina at in various capacities. So these are engineering products which we have made, which generally the high purity aluminas, the special products, they can be used in this special applications such as ceramic walls, in alumina substrates for electronic circuits. They are used in high purity alumina ceramic products. So thank you all for the patient listening, and this was all about special hydrate and alumina and the data which we have been able to generate, which we have been able to work upon has been mentioned in this presentation. Thank you all very much.